So I'm going to continue today with chapter 11, section 11.2. We're going to discuss inverses of functions. So let's first recall what the definition of a function is. A function is a set of points or ordered pairs x, y, whereby for each x value in the domain, for each x value, which is the first value in the domain, there is exactly one y value. In the range. So a function with a relation or a mapping would be called a function if for each x in the domain in the initial set there's exactly one y. Each x has to be paired with exactly one y. Okay, if an x is paired with no y, or if an x is paired with two or more y's, then it's not a function. It has to be one x paired with one y. Does that mean every y has to be paired with one x? No. You could have, this is your x, this is your y. You could have 1, 2, 5, and then the y values are 3, 2, 7. You could have 1 is paired with 3, 2 is paired with 3, and 5 is paired with 3. As long as you don't have any x value making two or more relationships or no relationship at all. Each x has to be paired with exactly one y. A y can have one relationship, 2, 10, or none at all. Okay, and it would still be a function. So another example. So for the set of ordered pairs 1, 2, 2, 2, and 3, 2, as you can see. Is this a function? Absolutely. As long as no x value appearing, it's a function. But if you have G 1, 2, 1, 3, 7, 5, this is definitely not a function. It's just a mapping or a relationship. Why it's not a function? Because the 1, which is an x value, is paired with two different y values. That cannot happen in a function. Okay, what is one-to-one function? Now a function is unfair relationship where x has obligations but y has none. A one-to-one function, both have obligations. So if for each x there's exactly one y, and for each y there's exactly one x, so it's a two-way street. For each y there's exactly one x, then that relation is a one-to-one function. So in a one-to-one function, just like it says, for each x there's gonna be exactly one y, and for each y there's gonna be exactly one x. So each x is paired with exactly one y, and each y is paired with exactly one x. No x can repeat and no y can repeat. Okay, no x can repeat and no y can repeat. So 2, 1, 3, 1, 4, 2, although this is a function, but it's not one-to-one. Okay, it's not one-to-one because the y value of 1 is repeating with two different x values. You cannot have a one-to-one. It's not a fair relationship. Okay. Another example, f equals 2, 1, 3, 2, and 4, 3. You can see that no x is repeating and no y is repeating, so it is a one-to-one function. Okay, so we're given a set of ordered pairs. We can easily identify one-to-one functions. How do we identify one-to-one functions? If we have a graph identifying one-to-one functions given their graphs, we use what we call the horizontal line test. We use what we call the horizontal line test. You can see this is a function. It passes the vertical line test, but it doesn't pass the horizontal line test because this horizontal line crosses the graph more than once. For the same y value, there's two different x values. So if any horizontal line crosses the graph of a function more than once, then that function is not to one. Then that function is not one-to-one. So for a function to be one-to-one, no horizontal line can cross its graph more than once. No horizontal line can cross its graph more than once. So for any graph to be the graph of a one-to-one function, it must pass two tests, the vertical line test and the horizontal line test. Okay, it must pass two tests, the vertical line test and the horizontal line test. So for number 28, page 919 in your book, is this the graph of a one-to-one function? Here it is. You can see that this passes the vertical line test. No vertical line crosses it more than once, and no horizontal line crosses it more than once. So it is the graph of a one-to-one function. Let's look at number 32. A V-shaped graph is definitely not one-to-one because it doesn't pass the horizontal test. So although it's a function, but it's not one-to-one. Okay, it's not a one-to-one function. It does not pass the horizontal line test. If you look at a sideways parabola, is this the graph of a one-to-one function? It's not even a function. It doesn't pass the vertical line test. For this x, there's two y's, y1 and y2. So this is not even a function. Remember, a one-to-one function has to pass vertical line test and horizontal line test. Okay, so we know how to identify functions from a set of ordered pairs. We can identify one-to-one function from the graph. How do we identify one-to-one function given its equation? Identifying one-to-one functions given their equations. In order to do that, we use a t-chart, a t-table. For example, if I have, say, f of x equals absolute value of x, and I want to check if this is the equation of a one-to-one function. Is this the equation of a one-to-one function? Of course, if I can graph it and say it doesn't pass the horizontal line test, or I can do a t-chart. And you can see when you do a t-chart, you want to do a couple of negatives, 0, and couple of positive. Absolute value of -2 is 2, 1, 0, 1, 2. So you can see -2 is paired with 2, and 2 is paired with 2, so it's not one-to-one function. If you look at f of x equals x cubed minus 2, and you make a t-chart, you can see if you plug a couple of negatives and a couple of positives and 0, -8 minus 2 is -10, -1 minus 2, 0 minus 2, 1 minus 2, and then 8 minus. So you can see that different x gives you different y, so it's a one-to-one function. Alright, So now we're going to talk about the inverse of a one-to-one function. The inverse of a one-to-one function. So in order to start the inverse, I'm going to show you an example. Okay, example 1, and next to it, example 2. So let an example 1 f of x equals x. And let's get few ordered pairs. Like if I plug in a 1, for x, 2 times 1 is 2. If I plug in a 2, 2 times 2 is 4. 3 times 2 is 6. 4 times 2 is 8. And then 5 times 2 is 10. Now I want to do g of x. Instead of timesing the x by 2, I'm going to cut half, dividing it by 2. So let's see what happens. If I plug in a 2, gives me back 1. If I plug in a 4, it gives me back 2. If I plug in a 6, it gives me back 3, an 8, 4, a 10, 5, and so on. I'll just be content with 5 ordered pairs. If you notice these two graphs, the domain of f, which is, if we're only limited to these 5 points, 1, 2, 3, 4, 5, which is exactly the range of g. And if you look at the range of f, if we're limited to these 5 points, it's 2, 4, 6, 8, 10, which is the domain of g. So basically what we're saying here, x is y and y is x, right? That's exactly what we're saying. So in f, whatever it is becomes a y. You can see 1, 2, 2, 1, 2, 4, 4, 2. They're swapping x and y. Also, what's really important, if you do f of g of x, f composite g of x, look, this is f of x over 2, and you take this and plug it in there, 2 times x over 2 is x, and if you reverse that, g of f of x, if you plug f of x into g, f of x is 2x, you plug it into g, it cuts it in half, and gives you back f. So when you do f composite g of x, you do g of x, you get x. It's obvious from here, look. F of 1 is 2, g of 2 is 1. F of 2 is 4, of 4 is 2. If you reverse it, g of 2 is 1, f of 1 is 2. So it always takes you back to the original. So any two functions that have these 4 properties, where they swap x and y, and when you do the composite, nothing changes. F composite g of x, g composite f of x equals x. And functions with such properties are called inverse of each other. So we say g is the inverse of f, f is the inverse of g. Okay, they swap x and y. Whatever is x in f becomes a g, it becomes a y in g, and whatever is a y in f becomes an x in f. Notation for inverse: instead of writing inverse of f or g, whatever you want, we write f with an exponent of -1. Now remember, if you have a variable to a -1 exponent, that's 1 over x. But if you have a function to a -1, that's definitely not the reciprocal. What is that? The inverse of f, which means you're swapping x and y with f. Okay, that's what it means. We're swapping x and y with f. So for example, if f equals 1, 2, 5, 7, 3, 11, right away, its inverse, it's not the reciprocal, it's swapping x and y, so it's going to be 2, 1, 7, 5, 11, 3. As simple as, so when you have ordered pairs, to find the inverse, you just swap x and y. Now what happens when we have the equation of the function? How do we find the equation of the inverse? So given the equation of a function, find the equation of its inverse. All right. So these are the steps, and I'm going to show you examples. So the first thing is you're going to replace the original function, whether it's f or g, replace it with y. Okay, so for example, if we say find the equation of the inverse of f of x equals 3x minus 5 over 7. Find the equation of the inverse of f of x equals 3x minus 5 over 7. So the first step would be replace f of x with y. And you will see why we're going to do that. Because the second step would be swap x and y, or switch x and y. Remember what we said in the inverse? The inverse, all you have to do is what? Switch x and y. Okay, switch x and y. Right there. F, it's the inverse, okay? So x becomes y and y becomes x. So that's step 2, x equals 3y minus 5 over 7. And now we're going to isolate y. So if we have x equal 3y minus 5 over 7, to isolate y, you want to get rid of the fraction first. So we get 7x, so this is step 3, equals 3y minus 5. Add the 5, and then divide the 3. So this y that you got is actually the inverse function, okay? Y originally was f of x, we swapped it, it becomes x actually, so it's the inverse. Now let's see if it makes sense. Look, f, it times x, the input, by 3, subtracts 5, and then divides by 5. Times by 3, minus 5 over 7. So to reverse that, because the inverse is reversing what the function does, to reverse that, instead of timesing by 3, you're going to divide by 3. Okay, we're going to start backwards. So timesing by 3 minus 5 over 7. Instead of dividing the 7, we're going to times the 7. Instead of minusing the 5, a plus 5. Instead of timesing the 3, we're dividing by 3, which makes a lot of sense. Here's another example. So find the equation of the inverse, and there's always a test question like that. Find the equation of the inverse of f of x equals cube root of 3x minus 5. Find the equation of the inverse of f of x equals cube root of 3x minus 5. So the first step is to replace f of x with y. So y equals cube root of 3x minus 5. Okay, then you're going to switch x and y. So every y becomes an x, and every x becomes a y. And now we want to isolate y. Y is under the cube root, so we want to get it out by cubing both sides. So x cubed equals 3y minus 5. Add the 5. X cubed plus 5 equals 3y. Divide by 3. So y equals x cubed plus 5 over 3, and that is the inverse. Again, don't forget what inverse means. For every pair of points in f, in the graph of f, it's, if you flip it, it becomes a point in the graph of f inverse. Look, if you look at 2, 1, 3 times 2 is 6, 6 minus 5 is 1, cube root of 1 is 1. So 2, 1 belongs to the graph of f. Right away, without anybody telling me, 1, 2 has to belong to the graph of f inverse. Let's check. If x is 1, 1 cube is 1, plus 5 is 6, divided by 3 is 2. 1, 2 belongs to the graph. That's exactly at the core of the concept of the inverse, okay? All right, another example. Find the equation of the inverse of f of x equals 2x to the fifth minus 3. Again, we replace f of x with y. So y equals 2x to the fifth minus 3. We swap x and y. X equals to y to the fifth minus 3. We isolate y, so add the 3. Divide the 2. To get rid of the fifth power, we do fifth root. So y equals fifth root of x plus 3 over 2, and that's the equation of the inverse. Okay, so we know if we're given a set of ordered pairs, we know to get the inverse, we flip x and y. If we're given the equation, we go through these steps to get the equation of the inverse. What about if we're given the graph of a function? The graph of a function of f and the graph of its inverse f inverse are symmetrical about the line y equals x. Why are they symmetrical about this line and nothing else? Because remember how we get the inverse? We swap x and y. And why is that? I mean, look at, let me show you an example that we did earlier. F of x, f inverse of x. I'm going to graph both of them on my graphing calculator. F of x is, so we're going to go to y equal, we're going to do cube root. So in case you don't know what that is, it's math. Number 4 is a cube root. It's the cube root of 3x minus 5. And then y2, which is the inverse, it's between parentheses x cubed plus 5, right parentheses, over 3. If you graph these two functions, they're going to be mirror images with respect to the line y equals x. You're probably not going to see that right now unless you go back to y equal, go down to y3 equal, and then just put an x in there. And you're going to see how the line y equals x fits perfectly in there. So they are mirror images of each other with respect to the line y equals x. Okay. So if I give you a test question like this, if I say, so given the graph of f below, okay, here's the graph of f. Again, this is an example in your notes. So f has 3 known points. The first known point is -1, 1/2. The second one is 0, 1. And the third one is 1, 2. So this is the graph of f. It goes along the negative x-axis. And I want you to graph the inverse, okay? I give you 3 points. I say graph the inverse. So the first thing you want to do is flip x and y. It gives you a point on the inverse. So 1/2 -1. If this is 1, 1/2 -1. And then 1, 0 would become 0, 1 becomes 1, 0. And then 1, 2 becomes 2, 1. And you know, the line y equals x goes through 1, 1, 0, 0, -1, -1. If you draw that line, that's going to be your line of symmetry. And then you flip that over, and you're going to see this goes along negative x. So this is going to go along negative y through this, through that. And then through that goes towards the y. This goes towards the x. And this is the graph of the inverse. Okay, I want to show you one more. Again, given the graph of f, graph its inverse. So here's f. It goes through 1, 0. It goes through 1/2, 1. And it goes through 2, -1. These are the 3 points on known points on the graph of f. So I'll give you something like this. Okay? This will be given if I add something like this. So this is 1/2 1 1 0 and then 2 -1. Now I want you to do the inverse. So you start out with the reversing these values. 1/2 1 would be 1 1/2. So I'll use different color. 1 1/2. 1 0 would be 0 1. And 2 -1 would be -1 2. And the line y equals x goes through 1 1 0 0, so it's gonna be this line of symmetry, and the graph is gonna go through these 3 points. And you can see how it's symmetrical. Like this is a reflection of that, this is a reflection of that. Okay, so practice those, and that's all I wanted to do for now. So 11.2 is done.